they're like, can't we ever sell the same system over and over again? We say, well, every system is unique. Special airflow, special odor constitutes coming into it, special requirements for it. And so that's how we look at it with it, is that, hey, whatever you need, we can provide with it, certainly within reason. When we're looking at odor control, we're also focused on total odor control, not just H2S removal. So I think you'll find a lot of other technologies or other companies out there that are focused on that 99.9% H2S removal, but they'll leave you with CS2. They'll leave you with dimethyl disulfide because they don't know how to take that out of the air. They're very, very different gases. And so we've seen lots of cases where somebody bought a very nice odor control system and it did exactly what was in the specification and it reduced to hydrogen sulfide, but there was still a big odor coming off of the system afterwards. We also, in our design considerations, also talk about allowing for some flexibility, because as you guys know, when you're designing things, you have to make a lot of assumptions about what the odor is going to look like, right? Coming into the system. Is it going to be really high? Is it going to be low? Is it going to have these constituents to it? And so we always like to design systems with some flexibility so that we can make adjustments kind of on the fly after installation if we find out the conditions are different than what were assumed. And of course, when we're looking at design, we have to allow for access, operation, maintenance, and those things as well. We also have to understand the abilities of the maintenance personnel once in operation. That's a big factor. We see a lot of cases where certain technologies are put in with certain customers, and that customer has a very poor maintenance practices, and technology selected for that customer, which they are just simply not going to be able to keep up with. So for instance, a biological scrubber. Biological scrubber is not a really complicated system, but it does have pH sensors in it and has to be fed some nutrient and things like that with it. If that organization doesn't have those skills to be able, or interest in keeping up with it, it's going to be a big failure with it. So those are some of the things that we kind of see. When we talk about odors, these are some of the areas of odors that we look at and we ask about when people come to us. So we get fresh sewage odors. We get a lot of that, like with CSOs and things where there's not going to be a lot of hydrogen sulfide because it just hasn't been in the system long enough to generate much hydrogen sulfide, but there's still fecal odor involved with it. There's some type of odor with it. Hydrogen sulfide, of course, that's the primary focus in this industry. But that's the easiest one for us to take out. So we do that in our sleep. Mercaptans can be a real issue. These gases, mercaptans are a reduced sulfur compound, but they kind of looked at the same. But these other gases are reduced sulfur compounds. Some of these are extremely difficult to take out. They're certainly plain activated carbon doesn't work on all of these for sure. And they are also really obnoxious odors at very, very low levels, right? So hydrogen sulfide, everybody talks about, is that rotten egg smell, and you can smell it at pretty low levels. These are much worse. I think it's dimethyl disulfide is putrid garlic smell. We ordered some of that one time in a little bottle, and you could open it, and then the whole office would just be covered in it, and we couldn't get rid of the smell, for an hour or something. So you can get, and you typically will get these odors in a wastewater odor control system. And if you don't look to take those out, if you don't have specifications in there calling about actual odor reduction rather than just hydrogen sulfide reduction, you might end up getting those coming out of the system. Ammonia and amines, that's another odor that we deal with. We typically don't see those as big odor issues. Ammonia is actually an interesting gas, is that you can only smell it at really high levels. So everybody knows what, if you open a bottle of ammonia at home and you smell it, you know what it smells like. But it actually has to be like at 30 parts per million to even smell ammonia. And so typically all you have to do is flush ammonia with fresh air and it goes away real quickly. Nobody smells it. I mean, it's there, but it's at a level that nobody knows it. And then volatile organic compounds are another one that we deal with typically more in the commercial area than in wastewater odors. So here's some of those odors and some of their descriptions and their odor thresholds. But, the key to take a look at some of these things is, mercaptans can be smelled at 20 parts per trillion. Those are extremely low levels. Mercaptans are actually injected into natural gas. Natural gas doesn't have a natural odor to it. We actually put an odor into natural gas and into propane so that you can smell a leak with it. So that's why they use that, is because it can be smelled at very, very, very low levels. So those are some of the other odors. Here are some of the tools that are used. You guys are probably familiar with this. Tell me if you're not. I'll spend a little more time on there. But a Jerome meter is used for very, very low levels of H2S. Actually, these devices are now available in ppb levels. This is an Odalog. This company's kind of fallen by the wayside. They really haven't kept up with technology very well. There's another company, Acculog, that has come up as a really nice device, Bluetooth interface, very reliable. You can use these Draeger pumps to actually sample air and pull through these tubes. And then Tedlar bags, if you're not familiar with it, Tedlar bags and also Suma canisters are ways that you can actually collect air samples and send them off to a lab to be tested. So this is a lot of what we do when we're working with customers to define what their odor is, and then also to confirm that the odor control system works as it's supposed to. So let's talk about different types of odor control. So there are adsorbent systems, and in the industry, it's fairly common to call adsorbent systems carbon systems. All right. If you get one thing out of my talk today, what I'm hoping is that you'll understand that PureAir is not a carbon company. Chris said that last week. He said, "Oh yeah, PureAir is coming to talk about their carbon systems." And I had to cringe a little bit and say, "Well, all right, I got to educate Chris a little bit more next week." But anyway, when I saw him, so we consider ourselves. Well, first, we consider ourselves a air purification company, but the products that we use are what we refer to as engineered adsorbents. All right, so we've got a facility in Atlanta, and half the facility is dedicated to building equipment, and the other half of the facility is dedicated to making these adsorbents. All right, so we actually have a facility where we're making these different types of adsorbents, and we'll talk about these and why you would use them and how they're different than that. So there's adsorbent systems, there's biological systems, there's chemical scrubbers. I'm going to talk about adsorbent systems, probably 80% of it, and biological system, I'm going to throw in 10 or 15% of it there. And I'm not going to really talk about chemical scrubbers because we don't really do them. And so I'm not an expert on them, and I'm not going to try to fake it. So let's. The big thing is all those technologies have one thing in common. They need some kind of actual contact of the air with some type of medium in order to take out the odor. So in a way, they have some similarities. That's just selection criteria. So here's a chart that we use a bit when trying to take a look at what kind of selection of odor, of technology is going to be optimal for a customer. So in this area where you get really low airflow and low airflow and low H2S levels, typically, plane activated carbon works pretty good. All right, if you've got really low H2S levels. In kind of higher H2S levels and higher airflows, engineered adsorbents work, and I'm going to talk about what our engineered adsorbents are and how they're different than activated carbon. When you get into much higher levels, what ends up happening is the amount of H2S is so high that your consumption of your engineered adsorbent becomes so high, even though they are far longer lasting than activated carbon, it becomes so high that it's just an expensive proposition for the customer to be changing it out all the time. And so typically, we look at using some kind of hybrid technology, which is either maybe a scavenger, all right, and this is what we refer to as a scavenger. It's a low cost, kind of low efficiency iron product, which just takes down the H2S level to a lower level. And then follow it by our engineered adsorbents to take out the rest of everything. Or we might do a scavenger followed by engineered adsorbents or a biofilter in this area as well. All right. Now, when it comes to really high levels, then we're typically talking about a bioscrubber. All right. And there's all sorts of terminologies out there about biofilters and bioscrubbers and biotrickling filters and such. But this is an engineered system to be able to take out high levels of hydrogen sulfide. But we will almost always take a bioscrubber and follow it with an engineered adsorbent system. And the reason for that is the bioscrubber is going to do a great job of taking, 200 parts per million down to 2 parts per million, but you still have 2 parts per million left. You still have other odors getting through. And so that's why we always put a polishing unit with our engineered adsorbent after a bioscrubber. We do, yes. So we actually have a product we refer to as the BEAST, and the BEAST stands for Biological Engineered Adsorbent Scrubber Technology, and it's a package system which uses a really, really high efficiency bioscrubber. But again, if you're starting at 100 parts per million, you get 99% efficiency. You're still getting that left. Plus, bioscrubbers can have some interruption in them. If somebody forgets to add the nutrient to it, if the water supply gets shut off, if there's a freeze in the wintertime, it's a living thing. And sometimes there's an interruption with that living thing. And so having an engineered system after it, engineered adsorbent system after it, is a great backup. It's a good partner for that bioscrubber with it. Bioscrubber also takes a couple of weeks to grow the biomass. And so in the beginning, having that engineered adsorbent system there to pick up that H2S for a couple of weeks, even though it's a high level, the engineered adsorbent will keep up with it for a couple of weeks, without unreasonable cost. And then it'll pick up any odor that's created by a bioscrubber, because keep in mind, bioscrubber is full of bacteria. So there can be some musty kind of smells coming off of a bioscrubber. Plus, a bioscrubber is not going to be real good at taking out reduced sulfur compounds and such too. So that's why we use that polishing system afterwards with it.
Since that biomass is taken on the brunt of the H2S, is that you have to regrow that like every 10 years?
It's continuously growing, and so that biomass. The biggest problem with the bioscrubbers is the material that the biological grows on. All right, so there's some, you can call them pawls or packing inside of the scrubber, and a number of people in the industry use a plastic type material that's in there, and that stuff works good for about 5 years, and then what ends up happening is it ends up degrading, because these bioscrubbers have a really, really harsh environment inside of them. Right, they're not only are they getting hit with hundreds of ppm of H2S coming at them, they're also in a highly acidic stream, because typically these systems are running at a low pH because the bacteria like to live in that low pH. And I saw one from a competitor that was using these kind of like foam cubes. And after a period of time, those foam cubes squat down to the bottom, and they squat so much they block the airflow through, and you end up having some problem. And so the biological is always growing. The bacteria is always kind of replicating and growing new bacteria with it. The big problem is what the bacteria is growing on has to hold up in that harsh environment. We use a foam glass for our biological to live on. We give it a 10-year guarantee that it's going to last, because it's glass. So where's it going to go, right? And it is highly, highly, highly porous. And that's really the name of the game in the bioscrubber industry, is the more pores you have, the more surface you have for the bacteria to grow, and the more H2S it can capture. And so surface area is without a doubt the most important part of the design of a bioscrubber. The more surface area you have, the more bacteria you have, the more contact time you have with the bacteria, the more efficient it is, the more reliable it's going to be, that kind of stuff. And what you don't want to have to do is 5 years into this, tear that bioscrubber apart and put new packing in there. And you'll see some manufacturers that make it really easy to replace their packing in their bioscrubber, because they know you're going to have to do it on a regular basis. So those are kind of recommendations that we make on odor control. So let's talk about adsorbents. That was that first category we talked about. So this is the slide where I like to separate ourselves from the carbon guys. So the types of adsorbents that are out there are basically three groups. So there's activated carbon, all right? Activated carbon is a great product, been around for a long time. But it's good for general odor control, and it's really good for volatile organic compounds because it attracts other carbon molecules. So volatile organic compounds have carbon built into it. They're really great. It's not very good for inorganic gases like hydrogen sulfide. It can work, but it generally has a very low capacity to it. And let me mention to you about activated carbon. Plain activated carbon works on a mechanical principle, actually. The gases go into activated carbon, they get stuck in pores, but those gases can come back out. So with a change of pressure, a change of temperature, a change of humidity, those gases will desorb from activated carbon. So plain activated carbon in the wastewater odor control industry generally is not a good product at all. And it doesn't work very well. And it also doesn't work in high humid environments very well. Well, I can't think of a more highly humid environment than a wastewater odor application. Engineered adsorbents, the stuff that PureAir is famous for, uses a principle called chemisorption. So we use these little beads that we make that are basically little ceramic beads, or they're made from various, but they're highly porous from a microscopic standpoint. But we add a chemical to it or a catalyst to it, which makes the reaction of the capturing of the gas permanent. So when the gases go into this, there's no way for them to come out, all right? We also modify some of these to focus just on one particular gas too. So for instance, this product, which uses activated carbon in its formulation, but also has a catalyst added to it, this is called Sulfazorb XL. It has a capacity of about 66% by weight, right? It's like a for H2S, it's like an H2S sponge. When you compare plain activated carbon, that's kind of like 5% by weight. So this has got like 10, 12 times higher capacity for hydrogen sulfide with it. So you can see, well, why would you use this when activated carbon's a whole lot cheaper? Well, this has 10 times the capacity. So unless activated carbon's 10 times cheaper, it's probably not going to be the right selection with it. Not to mention you'd be changing it out very often. So we have all these different types of adsorbent medias. We don't have to get into exactly all the selection that we have, but there are adsorbent medias for specific applications. There's some for broad range applications. And then the last one is scavengers. Scavengers, I mentioned, are these. These are somewhat like the engineered adsorbents, except basically that is just iron oxide and some clay put together. And it's just used as a sacrificial kind of pre-filter before an engineered adsorbent system. Who would want to use that? Well, customers that don't have great maintenance practices, or have really cold climates, or have seasonal high levels, find this to be very attractive, because if you put a bioscrubber there to take care of the 50 parts per million that they have coming into the system, the bioscrubber is going to, first of all, the bioscrubber is going to be pretty expensive up front. But second of all, it's going to require a significant amount of maintenance. If you have it in a cold climate, you got to freeze protected in the wintertime and everything as well. And so there's a significant maintenance portion to it. This product is used like an activated carbon system would be, where you're just running air through it, and it's just naturally going to take it out. And it's far, far cheaper than the engineered adsorbents. And so the customer is able to just kind of keep changing that out, and then using the engineered adsorbents to capture the polish out, to capture the rest of the odors afterwards. So it reduces the overall cost of ownership. Yeah, that's a good idea. Yeah. So it's, like putting an anode on your boat hull or your engine or something. Yeah. So this is what activated carbon looks like. If you looked at it kind of under a microscope, actually, this is what it looks like under a microscope, but this is a visual of it. So gases, it uses the principle of adsorption. Gases go into these pockets and they get stuck in there, but they can get unstuck. Chemisorbents or where gases go into the inside and they actually react and they turn into a solid on the inside. And typically it's some type of a salt is what the chemical category is. It's non-toxic, non-hazardous. And the beauty of this purple product here is it actually changes colors when it's used up too. And so if you use this product in the system, the customer can actually grab a sample of the adsorbent, look at it, and if it's still purple, then there's still life left of the system. And they can kind of judge how much life is left with the adsorbent system. I'm going to accelerate us a little bit on this stuff. So activated carbon, we're not going to go into too much detail on that. So engineered adsorbents, there's all sorts of bases. There's two parts to engineered adsorbents. There's substrates, and that's the porous part that is holding and capturing the gases. And then there's the impregnates, or the additives to it, which are going to be canceling basically, or reducing the gases that it captures. So there's various caustics and acids and oxidizers and catalysts we can use. This is the one that I mentioned that changes colors, but we also can blend them together. So sometimes, for instance, we use this product as a combination of the purple product and plain activated carbon as a polishing, as a final polishing step in our wastewater odor control systems, because this product overall does a pretty good job in catching those mercaptans and dimethyl sulfides and things like that. So we can blend these products together to provide some specific benefit. This is that scavenger. We call this Sulfazorb Fe. Fe is just for iron. With that, just as a nod to its iron chemistry. So typical adsorption system here, mist and grease filter. I can't stress to you guys enough about how important a mist and grease filter is before an adsorption system. We have retrofitted many of our competitors' systems who did not put mist and grease filters on the inlet of their system. Keep in mind, these systems run 24/7. And even though it doesn't look like they're pulling in a whole lot of water, if there's any kind of mist, it's just going to pull it in and pull it in. And water droplets, not humidity, but water droplets are really one of the most harmful things for adsorbent media. Activated carbon, engineered adsorbent scavengers. You don't want liquid water to get into that, because that liquid water gets into those pores and it clogs them up, and it's just not going to work very well. It creates a real mess. PureAir makes small systems. We call these drum scrubbers. These are kind of in the budget area where if a customer needed to order something real fast on a credit card, they could kind of do that. This is the time of year we get a lot of orders for these systems as things are warming up. We have fiberglass systems. This is a specialty system, a horizontal flow system with two individual beds here. So we got a 24. So well, let me back up. First, there's an integrated mist and grease filter. And then there's one adsorbent bed here that's 2 feet deep, and there's another adsorbent bed here that's 1 foot deep. So we can use two types of adsorbents and independently change them if we have to. And here is a fan section, enclosed fan section, super quiet fan. So it makes a really nice quiet system with there.
So that would you use if you're trying to.
Yeah, so almost all of our systems, I mean, we very seldom have a customer that says, I only have one gas that needs to be removed. He may say, this is the primary gas that I have to be removed, but we also have these other things. And certainly, without a doubt, wastewater odor control is one of those applications. So here, we would put a bed of our H2S catalyst adsorbent. It's called Sulfazorb XL. It's that one that's 66% capacity. And then afterwards, we would often put that blended media to capture those mercaptans, just those other odors with it. Very, very, very effective in doing that. Typically kind of a 2/3, 1/3 ratio with it. But we could do kind of any ratio that you want. In fact, we just installed a system in Portland, Oregon, where the customer was so nervous about his mixture of what adsorbents he was going to have to use that he asked us to design a system where those beds could be moved actually, and the ratio changed. So they could go 25-75, 50-50, 75-70, 25, like that. It turned out in the end they only needed one type of media, but that's the kind of things that we can do, is prepare you for the unknown. This is the mist and grease filter that we provide. Highly efficient at capturing this. So this is a test you can see we're doing where we're just injecting some fog basically into the system. That fog gets caught in this mist and grease pad, and you'll just see a constant trickle of water coming out of the system and nothing getting through. Highly efficient at capturing that fog, but then it's also capturing grease inside of it and kind of dirt and stuff. That's stuff that you don't want to get into your system because it creates a mess with that, oils and fats and all that stuff. So this filter, the water will drain out. There'll be a drain at the bottom, so the water is the easy part of it. The misting, the grease, we'll have a differential pressure gauge on this. So when the pressure gets up high enough that it's clogged, it's clogged up, then you've got to take this filter out. Typically, we recommend the customer has a spare set of filters, but every kind of couple months, they have to pull these out and then just hit it with a hot pressure washer and break up all the grease and dirt and get it out of there and then put them back in. So this is a permanent filter, but it does require some cleaning every once in a while.
What's the typical operating pressure on that?
So we change it out. When it's clean, it's a 1/4 inch. When it is dirty, I mean, you can change that whenever you want, but we typically say change it out when you get to 2 inches. So here's an example of some of these beds that we have where they're separate. You can see the difference in the absorbent media there with it. So one of the things too that I want to mention to you is, what's the difference with PureAir? Well, again, we're not a carbon company. We're not a fiberglass company. We actually make systems out of fiberglass, HDPE, stainless steel. Some customers want it. We have in some of our markets, like in the indoor air quality market, we'll make it out of painted steel, right? Because it's not a highly corrosive environment. We're taking out gases that aren't corrosive. So we have lots of different materials. So we make all these custom systems, but one of the big advantages that we have is because we understand the adsorbents and because we're using our adsorbents, we have ways for the customer to monitor his system, all right? So if you talk to the other guys who are out there, who are the fiberglass tank guys who just put carbon into their fiberglass tanks, you'd say, well, first, how long is this going to last? And then second of all, how do I know when to change it out? And they'll be like, well, when it starts to smell, change it, okay? Well, that's not the most productive thing in the world. I mean, you take a look at today's supply chain interruptions. If somebody wanted to place an order today of activated carbon, which, by the way, almost none of the activated carbon is produced in the U.S. any longer. If it's coconut shell, it's coming from India or Sri Lanka or something. A lot of the coal-based activated carbon is coming out of China, and so there's huge supply interruptions for that stuff. But if somebody suddenly had an odor coming through their carbon system, they right now they have to call. It'd probably be 6 weeks that they're going to have odor coming out of that system before they can get product in for that. So we have systems that prevent that. So this is a short version that I can travel with on an airplane of our real-time media bed monitor. So this actually goes into the side of our systems. This picture's kind of turned a little bit. It goes in at an angle into the side of our systems. And this rod starts off in this color, and then as the adsorbent media is consumed, our adsorbent media is consumed in a band from the inlet to the outlet, all right? This rod will actually change colors. This has been painted for dramatic effect, but it'll turn black. And as that rod, which is typically 3 feet long, as that rod progresses along with it getting blacker and blacker with it, you can pull that rod out and document once a month how much of the rod has progressively gotten black, and that will give you an indication of when you need to change it out. So we kind of call this the July 3rd rod, because for the guys out in the field that are responsible for these systems, it prevents that whole situation where you're hooking up your boat to your trailer, you're about to head off, and the boss calls and says, hey, the odor control system down by the park is giving us trouble. Can you go down there and check it out, right? You would know months ahead of time when the odor is going to start breaking through if you had this device on there. Okay, so we've had this device since the incorporation of the company. We're a 17-year-old company. We've had this from day one. It's a great device. Nobody else offers it in the market. It uses a special bimetallic alloy. Nobody else has figured out how to do it. We're happy that they haven't figured out how to do it. But we've had a lot of customers that have come to us and said, well, can you do that electronically? And for many years, I was like, no, it can't be done. No, it can't be done. Well, finally, after thinking about it a lot and such, we kind of had a eureka moment. We were able to figure out how to do that electronically. And so we developed what's referred to as the electronic bed monitor. So this is basically the same rod. This has actually evolved into some different form. We actually have a new version coming out in August as well. But this is basically the same rod, the same concept where we're taking a rod and we're going down through the adsorbent media. But what we're doing is we have these sensors here, which are basically the same concept here, and these sensors detect as the odors break through, and they're feeding it back to this PLC, and the PLC looks at it and says, "Oh, sensor 1 is detecting odor. It's been installed for this long. It's now detecting odor, so we know that we can kind of start to predict out the life of the adsorbent media." And then as sensor 2 comes, the system gets smarter and smarter. It's collecting this data, and it keeps updating the data, and it feeds back information to the customer. It has a 4 to 20 milliamp output, so the customer at any point in time can know how much life is left in his adsorbent media. Odor control systems are basically the last systems in the wastewater odor control field without any type of monitoring on them, right? If you think of, people put activated carbon systems out there, you've got every other piece of equipment at a wastewater facility has some type of electronic monitoring to indicate whether it's working or not. Odor control systems in the past is the fan on or is the fan not? That's the most that you were able to kind of do with it. Or even if you put H2S monitors at the inlet and the outlet, all that does is let you know that it has broken through, that it's no longer working. It doesn't give you any predictive value to it. And so this electronic bed monitor is a super nice product. We are also licensing this to others to be used as well. And it can also be retrofitted onto other systems as with it. So if there's an existing customer that's having a problem, wants to know about it, we can actually install this onto his system and put our adsorbent media in it, and it works very nicely. So biological odor control, I'm going to try to get this wrapped up by 1 o'clock. So biological odor control, we break biological odor control up into biofilters and bioscrubbers or biotrickling filters. Unfortunately, there is no standardization in the industry on these terms at all, but I just want to describe how we look at these. So biofilters are what this is, and what I don't want to, I guess we'd call these kind of dumb systems, all right? So this is some type of a container, and it could be a big hole in the ground, it could be a concrete prefab system, it could be made of all sorts of things, but it's typically filled with bark, mulch, coconut husks, all sorts of different materials. But you'll basically take your odorous gas, you're going to percolate it up through the system at a very slow rate, and it does a good job at capturing H2S. It's a fairly low cost system. Generally, it's not a good system for high levels of H2S. These systems, 5 parts per million, probably pretty good. Beyond that, I'm not sure that they're going to be as effective for you with it. But generally fairly low in maintenance. You just have to kind of keep the bark, the mulch humidified with it. There are some people out there that have special bark and special mulch that have special powers, I guess, I don't know. But this is a typical biofilter. Schematic for a biofilter is pretty much a blower in front of the system, a humidifier that's making sure that the air going into the filter media, into the bark, is very humid, because the bacteria that are growing on that bark need that humidity. A way for water to come out of the system. If this is an open area system, you have to be careful, because rain is just going to pour into it and it's going to fill this thing up. So you have to be able to drain the system, or even just the humidified air might collect in it. So that's a typical biofilter. A bioscrubber, on the other hand, is what I would consider an engineered system. It's typically a recirculation system. There's a packing inside of here. I mentioned our glass foam that we use. And we have sprays that are spraying a liquid, spraying the water onto the bacteria to keep the bacteria, wet with it. But there's also nutrient that's in here. So the nutrient can either be added artificially if you're using potable water for the system, or you can use some tertiary water that still has nutrient in it from the system. So if you're at the plant and you've got some water that's available, then that still has nutrient in it, then that can be used in the system. But generally, the H2S comes in the bottom, it blows up through the packing, and then it comes out the top. I was just at one of our latest installations 2 weeks ago in Illinois. We have 125 parts per million going in the system and 1 part per million coming out. And that was only after 1 week of operation. So that means all the bacteria hadn't grown, perfectly and everything. Usually it takes at least a couple weeks for the bacteria to grow real well. And so these are really, really nice systems. But again, we're still getting 1 ppm out, right? So that 1 ppm typically is not desirable with it. It's a huge improvement for sure. So comparison of biofilter and bioscrubbers. The biofilter is simple, typically low cost material, low maintenance, broad odor removal. It does work on more than just hydrogen sulfide, so it does provide some good broad odor removal. It's optimal for low odor levels, and you're going to typically need about a 30-second residence time. So there's a lot of size. There's a lot of volume that's necessary in order to make this work. A bioscrubber or a biotrickling filter, kind of more of an engineered system. It's really focused on H2S. There are some systems out there that claim to be able to take out broad range odors and such, but it's really, really, really good at H2S removal. There can be recirculation systems or once through systems. The once through systems are typically because the packing doesn't hold up. The packing that the manufacturing is using doesn't hold up well in a low pH environment, and so they end up using just once through water rather than recirculation. These systems in recirculation, the bacteria like to live in the range of 2 to 3 pH. And so if you have a recirculation system, you can maintain that pH, and the bacteria really like it and thrive in it and really eat the H2S up a lot. Certainly more complex. You've got pumps and you've got sensors and everything on the system. So there is more to it mechanically. Freezing is a big issue. We see a lot of people that want bioscrubbers because it's a green technology, but they're in Minnesota and the system's going to be outside, and it's problematic with that. So not only is it problematic because you have pipes and things that are going to freeze, but you just got cold air that can come in. The microbes themselves don't like to be cold. They like to be above 50 degrees Fahrenheit. So if you're not bringing in warm air into it, typically a sewer is going to be fairly warm, but you still have to be fairly careful about that. And typically residence time is somewhere less than 15 seconds residence time. We can actually get pretty significantly below that, but we typically target for about 15 seconds residence time to get from 100 and something down to 1 ppm with that. Here's a chemical scrubber, so a wet scrubber. I'm just throwing that out here. These are super complex. I shouldn't say super complex, but certainly more complex. You've got to have chemical additive going in all the time, adjusting pH and such. Typically, they're working with very hazardous chemicals like caustics and bleaches and such. They're really good to focus on one gas and a kind of constant level of gas they're good for. But the maintenance factor for these are very significant. Kind of a comparison of some of the technologies. I could forward this on to you guys.